Prefer to knock that down. All right.
Hi everyone, thank you for coming to see my senior project final presentation. For those of you who don't know me, my name is Garrett Moss, and this is my project, Script Tech. Just a little bit about me before I get into my project. I'm a senior. I've taken a couple programming classes. I took robotics freshman year, programming game design sophomore year, and then last year I took AP computer science. And next year I'll be studying astrophysics at the University of New Mexico with a full ride scholarship. I was also in Cyber Patriot 2 years, last year as well as this year. Just a brief overview of my project. I'm using a convolutional neural network for optical character recognition in Python. Now that probably sounds pretty complicated, but basically what it is a neural network, which is a specific kind of program that can actually learn. It's loosely based on a human brain because it's made of artificial neurons. And I'm using this for optical character recognition, which is converting handwritten or printed text into a computer-coded encoded document, such as a Word document. The inspiration for this project actually came from a really cool program someone made called MAR.io. It was actually a program that used neural networks and genetic algorithms to teach a computer to play the video game Super Mario World. And when I saw this, I thought that was really cool, but I wanted something a little more practical to use for my presentation. So I did some research and found out that handwriting recognition is actually a good use for neural networks. And being a student, I always hated it where you have to write a rough draft. It has to be handwritten, but then the final draft, you just have to type it again. So I decided, why not make a program that could do that for me? My 5 project objectives for this year were to learn the Python programming language, as well as how to implement certain libraries effectively. I wanted to gain a thorough understanding of artificial neural networks, specifically the convolutional neural network, which I'll talk about in a little bit. I wanted to identify effective methods of machine learning. I wanted to discover methods for separating individual characters from an image of text. And my last objective was to create a functioning program that converts handwritten text to a computer-encoded document. This is my logo for my company, Script Tech. When I was designing my logo, I based it on neural networks and the learning of them. The left half of the logo is looks like a normal human brain, which represents the biological basis of neural networks and how they learn, while the right half represents a neural network itself and how everything is interconnected, which again I'll talk about a bit later. The colors I picked were blue and green. Blue because it represents trust, dependability, confidence, and cleanliness. And green represents growth, development, as well as nature and biology, which again is what neural networks are based on. My advisory committee includes my expert advisor, Patrick Berenger. He's a software engineer. Unfortunately, he was not able to be here today. My support advisors are my mom and my dad, as well as Sam Mock and Ivan Krukov, who are 2 of my close friends, as well as fellow senior project students. Now, getting into my research here, the main thing I had to research was neural networks. I researched a lot of different types, but for neural networks in general, they're just programs that use some really complicated mathematical computations to be able to learn over time, which is a lot different from a normal program. There's a lot of different kinds of neural networks, but the kind I specifically decided to use, and we'll talk more about in a little bit, is the convolutional neural network. And all neural networks are made up of artificial neurons, such as this sigmoid neuron. And as you can see, there are a bunch of inputs to the neuron, denoted by these X's, and then each input is multiplied by a weight, W. Now, that's all good. You have a bunch of inputs, they go into an activation function, but why is that important? Well, because a neural network is really just a bunch of math, multiplication, and functions, this means we can treat it like a math problem and just try to find the smallest error possible, which means the highest accuracy for the neural network. One of the common methods to do this is gradient descent, which is where you look at all those weights that are being multiplied together and you change something just a little bit up or just a little bit down, and then you see how that affects the error overall. You can look at this kind of like a ball on a slope. If you change it, you try to find how to change it so that it goes just a little bit down and eventually reaches this global minimum. which is the lowest error for the neural network, and therefore the highest accuracy. And for my project, I used a convolutional neural network, which is a type of neural network made up of a bunch of different layers that all serve a unique purpose. The input layer is simply the image you'll be processing. In my case, this is a picture of a letter or a digit. After the input layer, the first layer is the convolutional layer. This is where most of the calculations occur. Basically, what the neural network is doing is looking for specific patterns that make up different letters. Over time, the neural network can actually learn to identify what letter is what by comparing the patterns from different input images. After this, there's a rectified linear unit layer, which again sounds really complicated, but this is actually the simplest layer. All it does is take any negative numbers in the complicated math function and turn them to 0. This just makes it easier to work with and actually more accurate. Then there's a pooling layer. Simply put, it decreases the size of the data, throwing away everything that isn't important and only keeping the most important information. For example, if you have this 4x4 grid of numbers, and you take 2x2 blocks and take the largest number in each block, that gives you the most important information about that general area, but it really reduces the amount of data and makes it easier to work with. So in this example, you start with a 4x4 block, which is 16 numbers, and you end up with a 2x2 block, which is only 4. Because there's so many calculations involved in a neural network, decreasing the amount of data that needs to be processed is very important in making sure it can quickly process the information you need. The last layer of a convolutional neural network is the fully connected layer. This is where all the calculations that have been performed come together and produce an output that tells you what the letter is. The way it represents it is a probability. So for example, if you give it an input image that's the letter D, it might tell you the output could be the letter D is 0.97, the letter O is 0.7, and the letter T is 0.1 or something. That means it's almost certainly the letter D, but it could be the letter O, and it's definitely not a T. So because it uses this probability, it can account for letters that look similar by, instead of just giving you one answer, it tells you the possible answers and how likely it is that that's the correct answer. Because there's so much complicated math involved, I needed a way to do this that was easier for me. My solution was TensorFlow, a Python library for numerical computations. This means a Python library is something that basically gives you access to more functions instead of just being able to add, subtract, and multiply, and a lot of other stuff you can do. TensorFlow adds a lot of operations specifically for neural networks that makes the mathematical computations much easier to work with. So I don't actually need to know every single calculation that goes into the neural network. I can just tell it what I want to do when, and TensorFlow handles all of the heavy lifting for me. So the convolutional neural network that I ended up creating, I have it running on the MNIST database, which is a database of 70,000 images of digits, such as this. And 60,000 of the digits are used to train the neural network. This means telling the neural network what the output should be when you give it an image. So for example, giving it just this 3 and saying, this should be a 3. And if you do that 60,000 times, eventually it learns to recognize these patterns. Because it has so many examples, it sees all the 3s, what goes into making a 3. And eventually it recognizes these features and what makes up each number. But to make sure it actually learned how to identify these characters, we use the last 10,000 digits and don't tell it the output to see if it actually can come to the correct conclusion. On my laptop, this neural network took 40 minutes to train, and the final accuracy was 99.17%. Now that sounds really good, but that's mostly because the MNIST database is specifically designed for training and testing neural networks. Because in a real world situation, it wouldn't look necessarily like this. It's very simplified and clean for the neural network to easily process. However, if I did implement this, the accuracy would probably decrease, although I could expect at least an 80% or maybe 90% accuracy. The other important part of my research was thresholding. Because the neural network can only process one character at a time, I had to be able to take the characters, or take an image and divide it into individual characters. But it's a lot easier to do when the image is just black and white instead of all of these different shades. So thresholding is the process of turning a grayscale image into a binary image. So there's only black or white. Everything that's important would be in black and the background would be white. This is a lot easier to work with when there aren't all these shades. I used OpenCV, which is another Python library, to do the image processing. It adds a bunch of useful functions for even just turning an image to grayscale and then some adaptive thresholding methods. But I'll get into that in a little bit. So the simplest kind of thresholding is called the binary threshold. This is where you just take a grayscale image and compare each pixel to a certain value. If the pixel is darker than that value, it becomes solid black. And if it's lighter than that value, it becomes solid white. So for example, with this image, if the threshold was right in the middle, everything to the left of it, which is darker, becomes black, and everything to the right of it, which is lighter, becomes white. While this is the simplest method, it's not the best method because it loses a lot of the fine details that are important, especially when there are shadows in the text. For example, in this image of a Sudoku puzzle, there's a lot of different shades because the lower left corner is shaded a lot more than the upper right corner. So if you compare the entire thing to a single value, such as this, a lot of the image becomes solid black because it's just a little bit too dark. But if you try to compensate for that by increasing the threshold, you start to lose some of the important information like the lines here because the threshold is too low to account for them. The solution to this is adaptive thresholding. Adaptive thresholding is, rather than comparing the entire image to a single value, each pixel is looked at within a region around it and compared to the other pixels. So if a pixel is a lot darker than everything around it, it becomes black. And if it's a lot lighter than anything around it, it becomes white. This means that shadows are not nearly as problematic with adaptive thresholding than with binary thresholding. Because if a region of the image is shadowed, like this lower left corner, everything in that region is affected by the shadow. So the important numbers, or any in this case numbers, are still darker than their surroundings, so they become black, even though they are already really dark. This is an example of the image after I processed it with adaptive thresholding through OpenCV. So all the important stuff is still in black, and everything else is white. This is another example with some text where it's very heavily shadowed on the left. So a binary processing, or a binary thresholding process would turn most of the left half into solid black. And of course, that's not what we want. But with adaptive thresholding, the text is still a little bit darker than the background behind it, so the text is black and everything else is white. This is what I was talking about with text segmentation. Because the neural network can only process one character at a time, I need to be able to take an image and separate it into individual characters. For example, this example I found, each character is denoted with a box drawn around it, and then that image would be processed in the neural network to identify the character. I ran into some problems because with adaptive thresholding, I found that the image size was actually a problem I had to account for. So, because with adaptive thresholding, each pixel, it looks at a region around it, the size of the image actually matters, because if it's looking at a 10 by 10 region around the pixel, and that's a 100 by 100 image, that's a lot different from a 3000 by 3000 image looking at a 10 by 10 region around the pixel. Because I wanted to keep the same proportion of pixels compared, I had to develop a formula that accounted for the image size to change the amount of pixels being looked at for adaptive thresholding. So now onto my timeline. In the beginning of November, I was just getting into the general research. This is where I made a basis of understanding for the rest of my project. So I researched neural networks in general, as well as specific types of neural networks. And this is where I decided to use a convolutional neural network. I also looked at data sets, which is where I found MNIST, which I'm using on my neural network now. Then in December, this is where my timeline started to go a little bit wrong. Because when I originally created the timeline, I had a general idea of how neural networks work, but I didn't actually know what went into creating a neural network. So in my timeline, I had specific dates where I said I would work on parts of the neural network, but after I did some research, I realized that's not how you build a neural network. So for example, on December 14th, I said I was going to work on getting the input from training sets. You don't actually, when you're making a neural network, you don't take these different parts. Because TensorFlow has all these functions for working with neural networks, you don't actually have to design each of the individual sections by themselves. So I did identify and evaluate possible Python libraries. In my timeline, just to make it easier, I have everything in green highlighted as something I had originally planned to do and accomplished. Everything in red is something I had originally planned on my timeline, but I ended up not doing for different reasons. And then the blue here is something that, instead of what I had originally planned to do, this is what I ended up doing. So after I'd done some initial research in November, I realized that I needed to use a library to work with neural networks. And even though TensorFlow makes everything a lot simpler to work with, it's still pretty complicated by itself. So here, instead of working on the neural network, I just started researching TensorFlow and getting acquainted with it so that I could later create my neural network. In January, again, I had some parts of the neural network that I had thought I would be working on, such as making the learning algorithm. But because I now realize that that's not how it works, I, again, researched TensorFlow more and did some tutorials just to get myself used to working with it and using the functions how they should be used. And then in the middle and to the end of January, I actually did begin creating my convolutional neural network in TensorFlow. Then moving into February, one of the important things that I hadn't talked about before is implementing a function to save and load the neural network. Because the neural network, as I said, it took me 40 minutes on my laptop to train. If that model isn't saved, then every time I would run the program, it would have to take 40 minutes again just to train. And if you want to take a picture of a handwritten essay or something and convert it into a Word document, you don't really want to wait 40 minutes for every page. So here I implemented a function that after it trains, since it's all just a bunch of math, it saves those values to later be plugged back in so it doesn't have to train. And then I started working on something called TensorBoard to improve my neural network. TensorBoard is a graphical representation of the neural network, but I found out that this is not actually, it doesn't actually represent what the neural network is doing. It represents the parts of the neural network as a whole. So I actually couldn't use it for what I had originally intended, although I did implement it. Then in the middle of February, I began working on the adaptive thresholding, the other important part of my project. And I continued to research adaptive thresholding, finding OpenCV, which is what I ended up using. Then here in March, this is where I worked on I finished implementing adaptive thresholding. And I had planned to start implementing text and character segmentation. But this is where I found the problem of the shadows in the text and solved that with adaptive thresholding. And then the image size, I had to account for that as well. So that pushed me back just a little bit on my timeline. Moving into April here, I was originally going to be finished with adaptive thresholding and text segmentation, but because there was so much research that I had to do for neural networks that I hadn't accounted for, and the problem with adaptive thresholding that I had to account for the image size and stuff, I was still working on text segmentation here, and I actually didn't end up finishing that section of my project. I was going to work on my final presentation and board in the middle of April, but I ended up saving that for the end of April because I ran into another problem. When my original intent was to use ruled paper, for example, with a handwritten essay, it would be on lined paper. The problem with this is because adaptive thresholding compares pixels to those around it, the lines on ruled paper are actually darker than the paper itself. So this means adaptive thresholding will actually recognize the lines as important information, and that they'll end up black in the image. This ended up being a problem for text segmentation, because if there are lines in the image, it's hard to separate one line from the next. and still take into account all the lines in the middle. So near the end of April here, or oops, the middle of April here, I was researching methods to remove the lines from ruled paper, but it turns out that's actually a lot more complicated than I thought it was, and there are a lot of really complicated research papers about that, and unfortunately I didn't have enough time to work on that. Then at the end of April, I just worked on my final presentation and my board, and that brings us to today. So while the bibliography is going, any questions?
Okay. All right, thank you.
Oh, one question.
Who?
Yes, no?
No? All right. There's a tease.